So the talk today is going to be by, oh, so all my notes disappeared. Is going to be by, by Varun Gangall. So he's a PhD student at CMU and he's in the language technologies institute. And he's supervised by Ed Hovey. So generally been working on things having to do with language and language generation. And so he's going to talk to us today about a variety of those issues. So thanks. So I'll let you have the floor.
Yeah. So hi everyone, and hope everyone's doing well during what has been like a difficult period for everyone like around the globe. So thanks for giving me the chance to present here. And so in the first third of my talk, I'm going to be talking about how much BERT already knows about events, and I'll also give a primer on BERT for those who may not have heard of it yet. And in the second third, I'll be talking a bit about infilling abilities of BERT, like how well it can predict missing sentences. We already know it can predict missing words well, because that's how it's being trained. And in the third part, I'll be talking about data augmentation for generation, which is something we don't see so much. We often see data augmentation for classification more. So yeah, and you could also through these links go to the papers and check them out. And I also shared the slide link on chat. So yeah. So part one, yeah. So our paper has a rather loquacious or wordful title. And yeah, just to make the pun apparent, we have put the battering ram there. So this is going to appear at the third Black Box NLP workshop later at EMNLP. I'll also talk about this event specifically, like which relevance. So first up, I'll just ground the notion of what we mean by events in natural language processing. So you can see the sentence here. It's about Caesar's assassination. And what we mean by an event most fundamentally, so how it starts off is that there's an event trigger, which is basically some kind of action phrase. It can either be a verb or a verb phrase, but that's not necessary. It can even be a noun like gerunds and participles and things like that. These event triggers are typically pre-annotated in corpora, or you may also have some rule-based or machine learning-based approach. Same as how you detect entities, you could detect these event triggers. And once you detect the event trigger, you also detect the event type together with that based on some type hierarchy. So for instance, over here, we have an event of the type crime.murder. So once you have an event trigger with its type, types have some stereotypical frames associated with them. So this frame, you can think of it as a collection of roles associated with that event. And so you have these roles like killer, victim, whatever, location. And the arguments are like parts of the document which you have to fill up into these roles. So what event argument detection is basically concerns itself with is how you predict these arguments from the document and assign them to these roles. Why detecting events matters is you can think of it events as a higher level representation, which is even like at a higher level than the text itself. So if you have places like investment funds or think tanks or defense agencies, and they are trying to go through many documents at once, or sometimes they're even looking at live feeds where they have to act immediately, it's often not feasible to analyze qualitatively many documents. But if you have events, you can look at them more concisely. You can also then drill down to specific documents, and like once you see an interesting event. And there are many meta things you can do based on events, like you can construct timelines or approximate causal paths. So the meta tasks based on events are like, so the most fundamental one is event argument detection. But after that you have things like event co-reference. So the same event may be referred to many times over within the same document, even across documents. Like for example, back in this example, we had this assassination. So that's like a reference again to the killed. So that's like co-reference. You can also, like as I said, detect timelines. So killed comes before sparked, just as in here. So after Caesar's killing, something got sparked. I mean, see, since we don't go further into that document, but that's an event which followed the killing. But you can see that clean and precise event argument detection is fundamental to all of these. So that's why we are trying to understand how well BERT already knows about events. And what I mean by already know is we won't actually train BERT with supervision to do the task. What we'll try to do is we'll try to find what part of BERT is already well correlated with this. So, I mean, of course, we know that if you take BERT and you actually use a labeled set to fine tune it, it will do very well. It has been known to work well on most tasks. So the particular data set we'll be looking at is called RAMS. I mean, that's where our names comes from. Name comes from. So RAM stands for roles across multiple sentences, and this is by no means the only event annotated data set. There have been many more in the previous years. But what's good about this data set is it actually annotates arguments from other sentences. So you can have like instruments and places and things from other sentences acting as arguments to events in the current sentence, which is actually more useful when you're doing event detection in the real world. So for instance, here the specific sentence only talks about Russians bombarding a run-of-the-mill outpost, but the information about like that there was an aircraft and this was somewhere in Syria, that's located in another sentence. So earlier event annotated data sets didn't have this thing annotated. So that's why we picked this data set to analyze. And of course, it has a diverse mix of roles and stuff too. It's quite large, which is nice. I'll also go over what we mean by, so this already know thing, which is also known as probing. So why this whole set of activities or methods arose is because there was a transition in NLP, in the learning paradigm. So this occurred even in vision and many other fields. So before 2012 or 13, before deep learning really took off, what you used to have bags of pre-designed features which were based on intuitions either from linguistics, sometimes even statistics like TF-IDF, and you had non-deep learning architectures along with them. Then what happened in the 2013 to 2017 period is that you didn't have so much to design with respect to the features, because these were always like embedding matrices, sometimes pre-initialized, sometimes from scratch. But the main effort went into designing a particular architecture which suited your task, putting in your task knowledge into designing that architecture. And after 2018, what you have seen is you have seen the rise of these things called contextual embeddings. So what a contextual embedding essentially is that instead of just an embedding, you have basically an entire large model, which are like many of your lower layers, pre-trained on very large data sets or corpora. For your particular task, you then just take this pre-trained model and you just fine tune few additional layers on top of it using the labels you have. So so concomitantly, I mean, in parallel, there has been an increased urge to understand how much do these models already know without training about different aspects of language, and where does this knowledge reside? And how do you even formally make claims about where this knowledge resides? So this whole thing is called probing. And you can see that the black box NLP, this is happening for the third time. So this workshop is primarily concerned with probing. I've also heard that it may spin off into its own conference like this year or later, but I'm not sure. Anyway, so you can see that this has been taking off in terms of interest. So yeah, the very first works they looked at in this sphere, like probing, they looked at how well plain LSTM language models, how good are they at learning simple syntactic phenomena like subject verb agreement. For example, if you have keys to the cabinet, then you'd expect are rather than is to follow. So in this work, like they kind of just checked how well language models are at this without being like explicitly trained on such pairs. So they found that you do need to explicitly train them. Without explicit training, they can't do very well at this. This is another later work. So they looked at some other phenomena like reflexive pronouns like himself, and so whether you can predict the right reflexive pronoun given what's the current point you are in the sentence. So you should predict himself rather than themselves. So what they found is that the performance is good on local dependencies, but yeah, as you introduce more and more relative clauses, look, for example, the bankers thought that someone knew that something. So if you introduce more and more of these, then the performance drops. So I mean, I've listed here a few other good works in probing, but yeah, so this is the kind of stuff people have been analyzing in this regard. So before going into my specific work, I'll have a short primer on BERT and also transformers, since we are really going to dig into the specifics of this while looking at whether they look at argument, whether they understand events well. So BERT is essentially a transformer which has 12 layers and 12 heads per layer, and I'll explain what a transformer is up next. So and it's trained on, you can see lots of English text, so 3,300 million words. It And it uses something called masked language modeling. So what it does is basically it randomly masks out a few subwords rather in the sentence, and then based on the surrounding context, it tries to predict this. I mean, this is the loss function you use to tune your representation. And what has been found is that this works really strongly on a large range of on any downstream task. So if you just take this representation and fine tune it, it works really well on most downstream tasks. So now we'll break down what a transformer is and what we mean by heads. So you may have seen heads in the abstract. So what I mean by heads is specifically the self-attention layers of BERT. So these specifically are like pairwise interactions between representations corresponding to words. So you have k words in a sentence, so you have k squared interactions, and I'll explain how this layer makes these interactions kind of. So consider that you are entering the Lth layer of the transformer, the Lth self-attention layer, and your current representation for the ith word is EI. So the self-attention layer essentially has three matrices: key matrix, query matrix, value matrix, KQV, and you project EI to like KI, QI, VI. Now what comes in is attention. So what this attention does is it essentially takes dot products. So for each word you have a different way of thinking about all the other words. For each word, basically you get a distribution over all the other words, which is your alpha ij. So at the ith word, you have a distribution over all the words j, which comes from these queries. And so you use the ith query vector as the to kind of take a dot product with all the key vectors. And so using these pairwise attentions, you then aggregate all the other words and construct the next representation for this word. So the output representation for the ith word will come through a weighted average of all the other words values based on these attention values. And then finally, so how this works is this was one head, you have many such self-attention layers. So similar to how you have many filters in a CNN in vision, similarly, you have many self-attention heads, and all of these combine to give you like different views of how words think about other words. and finally you get the output vector. This goes through like 2 more layers, and then it loops back and you go again to the L plus 1th layer. So that's how a transformer, from starting from the bottom, it like goes through 12 such transformations and builds the final, like, so if you had 20, if you had a 20 word sentence or a 20 subword sentence, even finally you will get out 20 vectors essentially, which have, and there were 20 vectors at each intermediate stage as well. So we collectively refer to, so you have H heads at, so the at the Lth layer, the Hth head, we refer to it as QH, L, KH, L, VH, L. So we just call this the attention head, or simply the head. And the corresponding attention values are the attention map of this head. So intuitively, what the attention map at a particular head tells you is how important word I thinks word J is for computing its next representation. And from these mod H cross mod L heads, you get mod H cross mod L importance distributions. And unless the transformer is degenerate, which it's not usually, each of this head like roughly captures different aspects of language. You can think of it that way. We'll see that. So if you take BERT, for example, it has 12 heads and 12 layers. So in total, it has 144 such heads. We'll see how the into 2 comes about in a later slide. So one way of probing is that you look at these heads and see which of them correlate with the particular aspect you're looking to analyze for. So one of the first works to like propose this formalism was by Kevin Clark et al. So this was last year. So what they were looking at was dependency parsing. So dependency parsing is basically, given a word, you try to find what are its what is its verb, what is the pronoun which possesses it, what are its prepositions, things like that. So what they found is that without any explicit training, if you just, so if you are looking to find, so if you look at these figures which are from that paper, so if you look at the middle, if you, sorry, let me use my pointer. So for instance, if you are trying to analyze possessive pronouns, um, if you're trying to analyze possessive pronouns, and you're trying to see what it is that that the autograph is possessed by. So you can just take the attention map. So if you have alpha ij, you can take the I corresponding to autograph, and then you can try to find over all j's the highest alpha ij value. And what they find is that with very high accuracy, in one of those 144 heads, it will point to the correct possessor, like his and apostrophe s, or for plant its. So this is the head 7,6. So we have 12, so 12,12. So it can go from 0, it can go from 1,1 to 12,12. So head 7,6 corresponds to possessive pronouns, and head 8,10 corresponds to direct objects. So similarly, for each of the grammatical relations, you have a particular head that works reasonably well. So what we are going to do is, here is the same way these people analyzed it for grammatical relations. We are going to see if the particular role argument relations we were looking at, like for instance, as we saw for the Caesar assassination, location, place, things like that, are there like stereotypical heads which are always good at predicting these things? And we won't train BERT at all to explicitly perform event argument detection. So we'll just see how these heads do without any training. And yeah, formally, this is what we are doing. So one caveat here is that in parsing, dependency parsing, the answer is always a word. So what possesses you is just one word usually. But event argument spans, as we saw much earlier, event argument spans can also be multiple words. So you can have rebel outpost as a possible argument. So we make a simplifying assumption that as long as your head predicts one of the words from the span correctly, we give it credit. So how do we know that BERT BERT is doing like actually better than chance, like the best head we find is doing better than chance. So we have two random baselines. So the rand baseline is just pick a random token, random word from anywhere in the document, and sent is pick a random word from somewhere in the same sentence. And baseline 2 is stronger than baseline 1 because, as I said, I mean, even in this data set, 75% of the times your arguments lie in the same sentence. So yeah, I had mentioned about the into two, like how there are actually 288 heads and not 144 or 12 into 12. So far we were talking about alpha ij, where we were taking, so our word of interest was word I, and then we were seeing the distribution over the j's. But what this does is it kind of overlooks one triangle of the attention matrix because those attention values need not be symmetric. So if you go from the if you take the transpose, so the alpha ji values, you can normalize them and you can get another set of distributions for ij. So what this gives us is, so we use negative indices for these. So the positive ones are the most obvious ones, where you plug in I and you actually look at the normalized distribution over the other j's. And this is something which is like the other triangle of the attention matrix. So we call the simple ones from heads, and we call these two heads. uh, and we use negative indices like just to relate them well. So yeah, so we'll be looking at all 288 of these heads and trying to see if they correlate well. For each different role, we'll try to see is there some head that correlates well with this role. So what we find is that for 5 out of 15 of these roles, the accuracy is greater than 40%. It's definitely better than much above chance. In fact, for most of the roles, it's 2 or 3 times better than chance. Yeah, so the worst performing is place, which is 17.77. We'll dig into a bit why. But for most of the roles, you can see like it's above 30, and for 5 of them, it's greater than 40%. It's certainly better than chance. So we can definitely say that there exists at least one head which has much above chance knowledge about a particular event role. And now so over here, we also look at where this knowledge is located, kind of. So what we see is that most of the best heads, they lie in the 7th, 8th or 9th layers, two exceptions being artifact and destination roles. So destination role is kind of like if you're describing a journey or a person or an object moving from an event concerning that. So for example, the relics were moved from Constantinople to Moscow. So the Moscow over there will be the destination. And actually the artifact will actually there be the relic. So, and what another thing we find that roles which don't actually occur in the same frame, their best heads often overlap. So transporter typically occurs in events concerning movement, while beneficiary typically occurs in events concerning where you are giving someone an award or a donation, or where someone is receiving a degree, or even sometimes something negative like they are receiving punishment. So typically for the same event type, you won't have a transporter role and a beneficiary role. So what we see is that they are efficiently kind of sharing heads in that case. um, Another thing we find is that whenever, so the 8th layer, the 10th head, uh, that particular layer, that particular head is the best head for a lot of roles, for 7 out of 15 roles. But conversely, what's happening is of these 7, only one feature of these 7 roles which use this head as the kind of best head. Of these 7, only one of them features in the top 5 performing ones. So what's happening is that this particular head from amongst those 288 is kind of being tasked with learning a lot about events. So it kind of has to learn about a lot of roles at once. And most of the good heads are from heads, not to heads. So the stereotypical I to J direction is better rather than like the reverse one. So so we go from the event trigger to the arguments. So the arguments don't typically attend back to their triggers so well. So here are like two examples. So sorry for putting them this way, but the number of words were rather long, so this was the only way. So if you see, so this is a sentence about airstrikes during like the recent or like rather past 7 years conflict, like the Houthi and Yemen conflict. So you can see that it's something about airstrikes, but so this airstrike is like a trigger and one of the roles is target. So the one of the heads, the best head for target correctly picks out Yemen from amongst all of these. So you can see there are a lot of distracting entities down here. You have Saudi Arabia, you have dates like Saturday, you have Abdul Malik al-Houthi. So, but it kind of gets over all of these and predicts Yemen. And this is without any training. Another example is where it picks out companies for recipient. So this is about some agency or some brokerage agency or investment bank advising companies to do something. So for advice, the trigger, the recipient of that advice is companies. It correctly picks out companies. I'll also show you some typical mistakes. So over here, this is about renting. Uh, so someone rented a houseboat in San Francisco Bay, so that I think that person is named Heed, but instead of rented picking Heed as the beneficiary, it picks his, which is not entirely wrong. I mean, the his refers to Heed, but you can see even the mistakes make some sense. The second mistake, it doesn't make that much sense. So this is about someone serving as senator, and it also comes up in connection to I presume Bill Clinton interview because it's 2004, but the place should be New York because the winning was concerning a New York election and a New York senator, but it picks out Clinton. So presumably it's distracted because this is also an entity and it's concerned with the whole election. I'm not sure why this particular mistake occurs. So yeah, these were some qualitative examples. Uh, Now we'll also look at another approach which does a bit of learning. So actually, although we said we are not learning, we did do a bit of learning here because in order to see which is the best head, we kind of we didn't go over the training set. What we did was, so what people do typically in probing is they make the test set the training set and the training set the test set because you want to estimate over as less labels as possible, but you want to predict over as large a set as possible to get a more averaged out estimate of abilities. So yeah, we did use like the test set, which is like 10% of the available supervision to pick this one parameter, like which is the best head. But now what we'll do is we'll try to learn like a simple linear weighted combination of all these 288 distributions. So we'll learn these 289 parameters per role instead of, we were just learning one so far. So this does do a bit of learning, but in a very minimal kind of way. And note that while doing this, we don't update BERT itself, like the underlying representation. So those parameters are frozen. So you just take a linear weighted combination of those probabilities and then you renormalize them. And what we find is, perhaps it's expected a bit, is that linear improves this ability even more. So you go from like 40s to 50s and like 30s to 40s, mostly, apart from a few exceptions. So there's this role target, which we saw for Yemen. So what we see there is that the performance remains exactly fixed. So what we can conclude there is that that particular head, so layer 9, head 1, it's perfectly learning this aspect, and no other head is like significantly learning this aspect as well as this head is. So it doesn't have any advantage from like combining with another head to predict this better. Right. So yeah, so we saw these two approaches, best head and linear. We saw they are both above chance. We'll also now break down the performance like for different cases, how well this is doing. So the first thing is we look at is this is something we spoke about. So when you have event arguments lying in another sentence, so cross sentence arguments, how well do these approaches or like how well do they do? So what we pick is we pick the roles which have the largest fractions of cross sentence arguments. So these four roles are instrument, origin, participant, and place. So for place, we saw an example with Yemen. So you can see Yemen there could easily have lied in another sentence. And similarly, we saw for the Russia example, I think that the instrument was which was the aircraft over there. I think it was in another sentence. So these roles typically occur in another sentence or origin. Like, so when you have a document talking about, so did this missile originate from somewhere, or was this missile bought from somewhere? And then much later you'll have someone talking about whether the missile was used. So the origin lies in another sentence. So anyway, what we find is that if we look at the best heads, the accuracies sharply drop for the fraction of cases which are cross sentence. Like for origin, we see it goes to like sharp 0. For instrument, we see like it goes to 21. For participant, we see it drops by like almost 4 times. So you can see that the performance for cross sentence arguments is drastically worse. So what our hypothesis about this is that there are several within sentence phenomena. So BERT is not just looking at events, it's looking at a variety of things like syntax, semantics, it's looking at time, co-reference of entities. So what happens is that when the event arguments are in another sentence, there are several other within sentence phenomena which start reflecting more strongly in the attention values. So when you take the highest attention value, it's dominated by some entirely different grammatical aspect. So so the correct arguments can seldom dominate the attention values due to kind of occlusion from these other phenomena. So what we do is like, just for the sake of analysis, we make the unrealistic assumption that we know in advance when an event argument lies in another sentence. So for those cross sentence cases, what we do is we zero out attention values from within the same sentence. So what our hypothesis is that there might be perhaps another set of heads that are good at detecting cross sentence event arguments, and we try to find them using these cross sentence cases alone, using the same approaches as before. And indeed, like our suspicion turns out to be true. So if we do this, the cross sentence performance, it like for each of the 4 roles, you can see that the best head performance goes up. Like for origin, it's small from 0 to like around 5, but for instrument and for place, the jumps are quite drastic. And even for linear, if you take the linear method, this cross sentence occlusion does help for cross sentence event arguments, apart from one case which is for origin. So yeah, so what we found is that our like hypothesis was indeed true. So if you remove the effect of cross sentence attentions, then the cross sentence event arguments do correspond strongly to certain heads. This is our final like analysis. So what we look at is nonce performance. So I'll explain what I mean by nonce performance here. So BERT is trained on a lot of data. So so as we saw, 3,300 million words. So what might have happened is it may have memorized certain typical lexically frequent associations. So Russia is always a place. So if a certain event trigger is asking me to detect its place, then I need not really focus on the specifics of that event. Like if I see Russia as a token somewhere, I can just like point to it. So what we want to see is that is BERT getting are the heads getting the arguments right just by memorizing these associations, or are they actually looking at the specifics of the situation, like the particular event trigger given, what is the context, and by virtue of that they are predicting the argument correctly? So if our suspicion were indeed to be true, then what would happen is that if we perturb these arguments, so instead of Russia, if we give, so instead of Russia 15, if we give Vangia 24, which is a randomly generated word, so it most likely wouldn't have seen stuff like this during training. So most randomly generated words are not actually valid natural language words. So it wouldn't have seen this during training. So even after this perturbation, if it predicts the correct argument, like the correct location of the argument, that means that it's actually using the specifics of the situation to locate the information. In order to not change other factors, we hold the length the same, we hold the shape the same. So you can see that we maintain the hyphen and the numbers and the caps. So what we find is that for the best head approach, for about half the roles, they are somewhat robust to this kind of nonce perturbation. So the graph here basically shows us what was the delta when you use the nonce approach. Like, does the nonce, under the nonce perturbation, does your performance reduce? So if it's negative, that means that it's getting hurt. If it's negative and like below 2%, say, otherwise it's not getting hurt that much. So we can see that for some roles, surprisingly, it even helps. But for about 5 or 6 of these roles, it does hurt. This perturbation does hurt. So these are like artifact, instrument, and origin. The other half seem to be robust. But if we go to the linear approach, this seems quite robust to nonce perturbations. So only 2 of the roles have like a drop in accuracy when you compare. Yeah. So the conclusions.
So so do you think I can ask a question about this?
Yeah. Sure.
So why is this viewed as bad? Is like the fact that it has somehow memorized that Russia is a place.
Right.
So is this inherently bad? Or is this...
No, I don't think it's bad, because ultimately, like, for the real task, you want the model to use like a combination of its common sense knowledge and its instance specific knowledge to make the decision. But what we wanted to see here is like how much of this ability, we wanted to kind of isolate how much of the ability comes from common sense knowledge and how much of the ability comes from the instance specific knowledge. So yeah, you're right in the sense that learning these associations is actually not bad. We would want the model to have common sense knowledge as well.
Great, thanks.
Yeah. So yeah, I mean, yeah, just to conclude, yeah, so we saw that they do have modest but well above chance ability, but like it's not phenomenal. And with like, if you learn linear combinations, it gets better. Yeah, so that, and yeah, for the cross sentence case, a separate configuration which you learn by zeroing out within sentence stuff works better. And half the roles are robust to nonce perturbations. If you go to the linear one, it's like 3/4. What more could be done? So what would be good is if someone looked at BERT's abilities on all those other event-based tasks and maybe use the observations from there to actually improve event argument detection approaches. So I mean, this was just analysis because we made quite a few simplifying and unrealistic assumptions while doing this analysis. So one thing I was thinking of doing is I was planning to skip to part 3 and then come back to part 2, because it might be a bit of a change and kind of more interesting, like unless that's not fine. Is it all right if I do that?
I think it's fine.
Yeah.
Yep.
Yeah. So yeah, so over here, what we were trying to do is like that. So you may have heard of data augmentation before. So like how you can expand your training set when you're short on training data, kind of by constructing new examples from real examples which you have. So here we were looking at how we can use, so how we could augment data for fine-tuning generation models, generators specifically, especially pre-trained generators like GPT-2, when you're trying to adapt them for a new domain which is low resource. Sorry about that. Yeah, so yeah, so the need for augmentation, why does it arise? So all of you may have heard of GPT-2 and now increasingly more even GPT-3. So once we have these large pre-trained generators which have better few shot abilities, so they can actually learn from very few examples. So they already have good abilities and you can use very few examples to fine tune them to do well at generation. But what this has opened up is you have many new domains and settings where it was totally impossible earlier to do any kind of generation, where people can and want to do generation, and you still need to do some extent of fine tuning. I mean, although they have better few shot abilities, uh, and without fine tuning, you can't pick up certain things like length characteristics. Like, so for instance, newspaper articles are maybe 300 or 200 words long, but tweets are 140 words long. So, and these pre-trained models are typically trained on one type of text. So if you take GPT-2, it's being trained on a corpus of Newswire and Reddit and stuff like that. So if you want to use it to generate tweets, then without fine tuning, its length characteristics won't match. It won't generate things which are of the length as a tweet. And other things like formality or the tense or the narrator type, like whether you have a first person narrator or a third person narrator, omnipresent or other type of narrator. Uh, so that's why you need to do fine tuning. But unfortunately, so when you have few examples, then you want to augment your examples. So you want to make a few synthetic examples and then add them to your training set so you can fine tune better. But unfortunately, most augmentation methods in NLP, apart from if you take specific tasks like machine translation, they don't focus that much on generation. Most of the focus has been on classification. This is also true of methods in the wider like machine learning universe. And one question that may arise is, why can't we use the same methods which we use for classification in generation? So the reason is quite simply that the nature of the loss function and the learning problem are quite different. So in classification, what we are doing is we are trying to maximize the probability of the correct label from a small label set. Like you have 3 labels or maybe even 10 labels given the input. So if you have a particular augmentation approach which perturbs x to x prime, since x prime goes into the conditional variable, there is more leeway for how noisy your perturbations can be, because it's the conditional, it's not like the output. So it doesn't very directly affect the loss function. And especially since we go through a lot of encoding, and so even if you perturb the input quite a bit, the encoder representation shift only slightly. This is true for classification, but if you have generation, the X is both the input and the output in some sense. So you are maximizing the probability of, say in natural language, you're maximizing often the probability of either the next word given the previous words, or the current word given both sides, or however you may factor it. But basically it's kind of a self-supervised setting and loss function. So your input or your X affects the loss and hence the learning directly. So your augmentations need to be way more careful. And another reason is that in generation, in classification, if you get better at accuracy, you get better. But in generation, it's not just the specific loss you have to improve, but you have to improve many competing metrics. So for example, you have diversity. So how diverse are the outputs you generate given the same input? And like, what's the coherence? So are the outputs you generate, do they maintain a consistent topic, or like do they drift apart a lot? And this affects training data augmentation, because methods which you introduce that are seemingly helping reduce the loss, they still could be degrading things like diversity. So for example, if you have like an augmentation methods where you replace words randomly by frequent words, what would happen is that perhaps that would improve your loss, like the likely this kind of likelihood loss, but it would sharply hit your diversity. um, so before going in a bit further, I'll just quickly explain GPT-2. So specifically, we'll be talking about fine tuning or like training on the domain, the GPT-2 model, which just GPT-2 stands for generatively pre-trained transformers. This is again a transformer model, but this transformer model only looks left to right. So it doesn't look at both directions, like BERT. And it also has 12 layers, a lot of parameters. It's trained on like Reddit and a lot of other web text, and it's trained like a typical language model, so you maximize likelihood of word given its left context. And it can be further fine-tuned by giving uh, appropriately constructed. So this is the pre-training, and how people typically use it for their domain is you give sentences from your domain. Like if you want to fine tune it for Twitter, you'll give it lots of tweets, but you can also fine tune it for other tasks, like if for other, like not just language modeling or conditional generation tasks, but all. So this is conditional generation, like where you're just giving the first part of a document and you're trying to make it complete the document. So this is the by now famous unicorn example. So this from OpenAI's, like the site where they first released it. So someone gives in this thing about unicorns and the antis, and then it completes it with like unicorns who are unknown to science. They speak in English. They are philosophers. So yeah, you can see that it's very fluent, but certain other things like the coherence and stuff are not that perfect, but still it's pretty impressive. Um, Right. So yeah, so our baseline here will be like, so this is an approach which is recent, but it's simple, but it worked for classification. And again, it'll show the point of how augmentation techniques proposed for classification don't carry over that well to generation. So the baseline we'll use here is something called easy data augmentation. So basically, this is a suite of 4 different random perturbations. So you either do synonym replacement, or you do random insertions, random swaps, or random deletions. And what these people found is that for classification, this works really well, although it's so simple and easy to implement. And they tested it out on 5 different classification tasks. So I'm only showing the graph for Trek from their paper. So you can see here that, so the blue curve is the one with, normal training, and the red curve is the one with augmentation. And even when you take average across the 5 data sets, you can see that the red curve always beats the blue curve. So for classification, this works surprisingly well. Our method is kind of related in the sense that we are also proposing like a suite of kind of random perturbations from which we'll pick one randomly and augment the example. But our ones are focused on being meaning preserving while changing one aspect. So we want modestly meaning altering perturbations which just change one aspect of the sentence. So you can see here that what synthetic noise does is that it tries to perturb the character form of few chosen words. So you have sick going to sick and overpriced going to over edge priced, or we try to replace synonyms. So this is similar to the earlier one. Uh, 2 other things we do are something called hyponyms and hypernyms. So hyponyms and hypernyms are like super like more granular and less granular versions of the same word. So hypernym is like bread pudding is a baked goods dish, basically. And hyponym is like one type of bread pudding is crescent roll corn pudding. So you keep the meaning mostly the same. You just try to, for few words, change the granularity. And semantic text exchanges, you try to alter the topic, but only on one aspect. So you have, so the original review was about food in general. You're trying to change it to something about just coffee. Or a better example is here. So if you want to change a pizza review to a sandwich review, so if you give, so you'll just try to replace pizza by sandwich, and we have a model which can then by itself like replace crust with bread type and topping with filling and pepperoni with salami. Uh, yeah. So yeah, these are the four types of perturbation operations we have, and for our augmentation, we'll examine how good each of these are and how good they are in unison as well. So yeah, I mean, you already got a hang of what these are. So what synthetic noise does is it just perturbs the spelling a bit. And why this makes sense is it already happens in most natural corpora. So there are spelling mistakes, there are dialectical variations, which are frequent in any natural corpora like Twitter or Reddit. So this is not that unintuitive to do this. What we do is, one thing we do is that we don't change the first and last characters, we only play around with the middle characters, because that's not typically something we do even in our natural mistakes. The WordNet based mistakes, as I explained, so synonym is obvious, but hypernym and hyponym are like from this WordNet tree you replace with more specific and less specific words. One caveat about these replacements, so we saw a point we made about that we have to take care about certain aspects not related to the loss, like diversity, like other metrics. So if our augmented examples are too similar to the actual example, what will happen is that the model will get overtrained and the diversity will take a hit. So to prevent loss of diversity, we do replacements only on keywords so that there is some change in the augmented example. It's not like exactly a near replica of the actual example. Finally, this method, which is called semantic text exchange, that's like replacing pizza by sandwich. So this comes from one of my co-authors' earlier papers, the model. And how we use it is we pick noun keywords. So like we pick pizza, or it will be something maybe like cafeteria. And we replace this noun keyword with a randomly chosen entity. So what we want to do with this is we want to alter the semantics, but only with respect to a particular topical aspect. And so for evaluation, we'll evaluate this on four different fronts, like four different dimensions. One difficulty with evaluating these kind of generation models is that unlike say machine translation, you need to evaluate how good it is on generating multiple continuations for each input. So you don't want it to generate just one good sample. You want it to generate a good population of samples given a particular input, because you're sampling, so someone else may get another sample essentially. So the first aspect we examine is like, do the continuations sound like good English? So over here we just use fluency, which also comes from a language model. But rather than just use perplexity, we use something called slur. So this is like perplexity, but it's like normalized to remove the effects of word frequency. So you won't get credit for just for using words which are very frequent. You won't get penalized if you use Haiti instead of France, for instance. That's what slur is. Uh, for diversity, we have three different metrics. So self-blue tries to find, so if you generate a population of continuations, so by continuation, I mean, like over here, this is the continuation and this is the prompt. So for each prompt, we generate multiple continuations and we test how good this entire population of continuations is. So what diversity measures is how diverse this whole population is. Does it vary significantly, or are you generating the same sample? And we want more diversity. So what self-blue checks is what's the highest blue with one of the other continuations. So lower the self-blue, the better. And what unique trigram ratio checks is of all the trigrams you generate, what fraction is unique. So more of them are unique, the more diverse your generations are. Similarly, for type to token ratio, it checks in each continuation, are you generating new words or are you repeating the same words? So this kind of checks intra-continuation diversity. The first two check inter-continuation diversity. In any case, moving on. So content preservation. So the previous two things didn't check like about fidelity or faithfulness to what your original input was. So this is what content preservation checks. Like, do your continuations have content related to the given prompt? We use a measure called BERT score for this. Like, it measures how strongly the BERT embeddings of the prompt and the continuation align. And finally, we check, so the domain we worked with here were Yelp reviews. So Yelp reviews also have sentiment. So what we kind of checked is that for the complete population of continuations we generate, do they have consistent sentiment between each other, and also sentiment that's consistent with the prompt. And finally, so yeah, I will break apart this table. But finally, what we see is that synthetic noise, which is like, so we have two baselines. One is you just train without augmentation, which is gold. And random trio is basically EDA. That is like those three random methods, like random insertion, random deletion, random swaps. And what we find is that on all the metrics, synthetic noise, which is where you just vary the character form, and hypernyms, which is where you replace words by their less granular parents, like dollar and currency, or like coffee and beverage. Those two particular types of augmentation, they improve on all the four aspects, like consistency, content preservation, diversity, and fluency. So for fluency, if you see, synthetic noise and hypernyms are both kind of above the baseline gold level. And from the table, you would have seen that they are better than the random trio as well, like the EDA, easy data augmentation. Even for diversity, we see, so here self blue, the lesser it's better. So synthetic noise goes quite low. Hypernyms also manages to, it's just above the gold level. Similarly, for the trigram and type 2 token ratios, preservation. So first discussion is, why do hypernyms perform much better than hyponyms? So our conjecture about this is that hyponyms, they sometimes introduce esoteric and kind of rare words, since they are the more specific words, which seldom occur apart from really specific context. Like they'll replace dragon with, say, wyvern. So wyvern is like a specific type of dragon which occurs maybe in Welsh and other types of mythology, and it's not so frequently associated with other like myths or other dragons. And Kiribati dollar, which is the currency of a Pacific nation, but it's not something that you typically see in the context of money or dollars. Whereas if you see hypernyms, they go in the reverse direction. So you'll always go from like tea to beverage, or like dog to mammal, mammal to animal. So you're always going to words which are actually pertinent. They do occur in context. Another reason is that when you replace by a hypernym, you maintain the faithfulness. So whatever was employed by your original example, it still holds good for this. So if 3 dogs walked home, 3 animals did walk home as well. But if 3 dogs walked home, that doesn't mean 3 Dalmatians walked home. So when you replace by hyponyms, you kind of violate faithfulness a lot more. Another thing is, so one other suspicion one may have is that the synthetic noise, which kind of perturbs characters, is it kind of cheating its way to diversity by just changing around characters? So to discount for this, what we do is we run a spell check on our outputs. So, and what we find is, so if this were true, then synthetic noise would have way more spelling errors than the no augmentation case. But what we find is that in fact, synthetic noise reduces the spelling errors. So having more spelling errors in the prompts and having correct continuation makes it correct spelling errors implicitly as well. And finally, we also do an experiment where we vary the amount of augmentation. And just to synthesize things, we like combine all our what do you call it, all our augmentation methods together while doing this, because otherwise you'll have 20 graphs and loads of experiments. So we are just looking at all the augmentations taken as a whole. So what we find is that basically our augmentations can give improvements up to 3x of the original training data. So if you go till up to 3x, you get improvements. But after that point, you start seeing the decline in all the aspects like fluency or diversity. For whichever one you see, like up to 3x, you get improvements. After that point, the performance declines, or like the game starts frittering away. Sometimes it even falls below the no augmentation case. So the conclusion is, yeah, we proposed a new suite of augmentations specifically tailored for the generation case. And we showed this does better than no augmentation, and also the random augmentations which have been shown to work well for classification, they don't work so well. At least they work worse than our method here. And finally, yeah, so moving on, I know I'm out of time. What more could be done is that our suite of methods was impoverishingly simple. So if someone would have better linguistically more driven approaches based on like principles like compositionality, that might help for generation. And yeah, I'm entirely going to skip part 2.
First Zoom call on photo.
Yeah.
Interesting.
Yeah. So yeah, that's about it. And yeah, glad to answer any questions.
So thank you. So thanks for the very nice talk.
So did you have any problem? Everything is going smooth?
Yeah, so
I have to enter the ID. It's just that you can't join, like you can't say join from photo. You have to enter the code manually. But
Yeah. So Amarali, do you have a question?
so I'm sorry if I missed this during your talk.
Sure.
But one thing I've seen in the augmentation literature is people do back translation. So they
Right.
translate to a different language like German,
Correct.
and they
Yes, yes.
translate back.
Right.
How does that compare with your methods?
Right.
So
That's
I
a good,
posted the
very
agenda. It's in the calendar.
right. So yeah. So back translate. Yeah. Right. So one thing we do mention this in our paper. So I think, or I don't know. So one thing we wanted to do is we wanted to. So one thing is back translation is a very strong and good method, and it actually might perform well even for generation. But there are certain drawbacks to it. One thing is that it assumes the presence of a translation model, and specifically a translation model which a translation model which works well for that domain. So what may happen is sometimes you may be doing generation for or a specific domain like medical or something like that. So the actual low resource domains which you see, I mean, Yelp is of course a synthetic setting which we employ for our experiments. But for a lot of low resource domains, what may happen is that your typical translation systems, which are trained more for the, what do you call it, social media or like book or like formal English or social media kind of English, they may not work so well when you input in those particular really domain specific text. And yes, it would have been nice if we had nevertheless analyzed back translation. Another thing we wanted to do is like we wanted methods which were just like easy data augmentation, really easy to like take off the shelf and implement. So translation models are of course also easy, but they are a bit more involved. Like you have to get English to French model working, a French to English model working, and you have to actually deploy it on a large number of examples. Not a large number of examples, but you have to actually run it. So you have to run decoding. Another thing that's been seen with back translation is that to get good performance out of back translation, it's not enough to just like predict one round trip example, but it's like kind of better to do beam search and predict, it's not beam search, like sample and predict like 20 samples, or like do beam search with a very high beam. So that is kind of computationally expensive. if you take the state-of-the-art translation models. So yeah, we wanted to try something which is really easy, so that just the way easy data augmentation was. But your point is completely valid. We should have also had back translation here. One thing is we did this work in a somewhat short span of time. So we were really constrained for time. Another thing is that we could have also tried syntactic paraphrasing, which is like you take the tree structure and play around with it. That is something we tried, but the specific approaches we were trying, they didn't give us good or fluent paraphrases using syntactic paraphrasing. But since we tried this, I think better methods have come out, especially in this time's ACL.
Are you referring to SCPN and SGPN?
Right. So I tried SCPN, but what I found is SCPN is okay, but it doesn't do that well for, at least for the examples generated, may be good enough for classification or like SNLI, things like that. But they don't, I mean, we didn't run full experiments, but they didn't do good enough to put into a negative likelihood loss. So just, yeah.
Yeah. I might ask you a few questions offline, but
Sure.
yeah, thank you for answering my question.
So yeah, since SCPN, there have been other methods. Like at ACL, there was a method from Greg Darrett's group which extends SCPN and makes it even better. So you could have in case you haven't seen that already.
I haven't had a chance to try it, but I've seen it's out. There's also this stuff like called SGPN, which is like based on exemplars, which seems very promising in the last few months.
Right. I think we are talking about the same one. Yeah.
Possibly, yes.
Yeah. Thanks.
So does anyone else have any questions? So if not, let's thank Varun one more time. So thanks for the great talk, and so thanks for coming here to present it to all of us.
Thanks for the opportunity, and yeah, thanks. I went like overtime, and so I hope I didn't like bore you, all of you, with the really
no, it was great. You covered a lot of interesting material. So
no issues, Varun. We were late also. We started late. No worries.
Yeah.
Nice talk. Thanks for presenting.
And yeah, glad if someone has more questions, feel free to email me or get in touch.
Yes, and if you have more questions, you can email Varun directly or even tell me. I can email. I can ask. No worries. Good talk. Thanks. Thanks, everyone.
Thanks.
Bye.
Within that, the sort of